chain of events, cause and effect. We analyze what went right and what went wrong, as we discover that many outcomes can be predicted, planned for, and even prevented. I'm John Chidgey, and this is Causality. This episode is sponsored by Extrasensory Devices and their amazing Luxi For All that no modern photographer should be without. We'll talk more about them during the show. Causality is part of the Engineered Network. For other great shows like Pragmatic and Nutrium, visit engineered.network today. On Friday, the 11th of March, 2011 at 2:46 p.m. local time, a magnitude 9.0 earthquake occurred under the sea at a depth of approximately 32 kilometers, 72 kilometers east of the Oshika Peninsula off Tohoku. It was the most powerful earthquake to ever hit Japan, and the fourth most powerful recorded since 1900 in the world. This earthquake occurred where the Pacific Plate is subducting under the plate beneath northern Honshu. Now, the Pacific Plate moves at a rate of 8 to 9 centimeters. That's 3.1 to 3.5 inches per year on average. And that movement pushes the upper plate down until the accumulated stress causes a seismic slip rupture event, otherwise known as an earthquake. If you haven't guessed already, we're going to talk about Fukushima. Now, the Fukushima 1 nuclear power plant consisted of 6 reactors, 1 at 480 megawatts, 4 of them at 784 megawatts each, and 1 at 1.1 gigawatts. Now, the design, there were 3 reactors online at the time of that earthquake. Those are reactors 1, 2, and 3. And all initiated a scram and a shutdown at the time that the earthquake hit. Now, SCRAM is an unusual acronym. In fact, some people have suggested it's not an acronym, it's actually a backronym, which is the phenomena where people will fit an expression backwards into an acronym to try and explain the existence of the acronym, hence backronym, kind of like that idea. Anyway, a SCRAM is supposed to be something like Safety Control Rod Axeman. And it was originally thought to have come, but the phrase was originally coined, apparently, by Enrico Fermi. And he was working on the Manhattan Project, on the Chicago Pile 1 reactor, and that was in the early 1940s. And the idea behind an Axeman is that there's a large collection of control rods suspended above the reactor core by a rope. And an Axeman, with an axe, is sent to cut the rope in the event of an out-of-control reaction. And this particular expression and terminology, method, whatever you want to call it, of doing an emergency shutdown of a nuclear reactor is primarily used these days for boiling water reactors, BWRs, like Fukushima. I don't want to talk too much about the different designs of nuclear reactors, but suffice it to say that a SCRAM is an emergency shutdown where you insert a large number of control rods into the core, so many so that it absorbs all the neutrons and completely stops the fission reaction. So, the plants are designed to initiate a SCRAM as soon as there is an earthquake above a certain trip threshold. This one certainly qualified, and a SCRAM was initiated on the online reactors. So, reactors 1, 2, and 3 were in operation, so SCRAMs were initiated on each of them. Now, within minutes, all those reactors were shut down. But reactors 4, 5, and 6, they were already shut down. They're in preparation for being refueled. And when you're refueling, what you'll do is sometimes the fuel rods will be withdrawn from the reactor and stored in a large pool. And in the case of Fukushima, it was in an upper level of the reactor building outside of the containment vessel. The exact quantity varies depending upon which reports you read. Some say as many as 1,533 fuel rods, some as little as 1,330. Irrespective of the number, let's just say a significant quantity, all of them, in fact, from reactor 4, they were in a cooling pool above the reactor, on the floor above. So the reactor 4 cooling pool was full of fuel rods that were not in use at the time of the incident. They'd actually been put there 4 months earlier, in November of 2010. Takes a while for them to cool down a bit. But reactors 5 and 6 were still in their reactors, and they had cooling water being pumped through them to keep them cool. So, back to reactors 1, 2, and 3. The earthquake itself doesn't, just because you have an undersea earthquake, doesn't actually mean you're going to get a significant tsunami. In this particular case, the break caused by the earthquake caused the seafloor to rise up by several meters, and that displaced an enormous amount of water above it. And liquids aren't compressible, so the energy had to go somewhere, and it travels away from that upthrust region as waves. The deeper the water, the shallower the waves, but as you approach shallow water, the wave height increases dramatically. In terms of the upthrust region, it's quite significant. The upthrust region was between 6 to 8 meters along a 180-kilometer wide seabed, and that was around about 60 kilometers from the shoreline on average. In fact, the tsunami was so significant it traveled as far as Chile in South America, and there resulted in a 2-meter wave height. Not enough to cause any damage, but certainly enough to be quite noticeable. And tsunami waves, of course, arrive as sets of waves. It's not just one. There's a subsequent series of them. But most tsunami wave heights are measured by the largest or tallest wave. But the first tsunami waves from this incident arrived at Kamaishi, and I hope I'm pronouncing that correctly. Apologies if I'm not. At 3:12 p.m. local time. The height was estimated at about 6.8 meters. They arrived at Soma at 3:50 p.m. with an estimated height of 7.3 meters. That's 24 feet. And this was around the time at which the tsunami also reached the Fukushima 1 power plant. At the plant itself, the waves peaked at a staggering 13 meters. That's 43 feet high. And that easily breached the protective seawall, which was only 10 meters or 33 feet high. Once the water had passed the seawall, the seawater proceeded to flood all of the low-lying areas of the plant, and this included the turbine hall and the reactor building. Cars and trucks are all swept away, overturned. The waves destroyed the pipework, and within minutes affected the backup diesel generators. And understanding why that's a problem, we first have to understand about fuel rod cladding and decay heat. So let's start with the cladding. Zircaloy, or alloys of zirconium, they're used predominantly in BWRs for cladding, as it has very low absorption of thermal neutrons, meaning they just pass through it and don't affect the material as they pass through. But it also maintains a high hardness, ductility, and it's corrosion resistant. And that's important because if the neutrons actually interact with the cladding material, then they will change what that cladding material is. And as you change what the material is, it changes its chemical properties. So you need something that's going to essentially be invisible, which is what zircaloys are, and that's why they are predominantly used in these nuclear reactors. But it's not all positives. Zircaloy also reacts with water and at high temperatures with steam. The oxidation of zirconium by water releases hydrogen gas as one of its byproducts. The other problem is that once it passes about 400 degrees Celsius, the oxidation rate increases dramatically. And that increased rate of release of hydrogen, for example, if you're in an enclosed vessel, which this is, will increase the pressure. As the pressure increases, that also further drives that oxidation process forward at an even faster rate. So essentially, the higher temperature leads to higher pressure. The higher pressure leads to a higher oxidation rate, which increases the pressure, which leads to a higher oxidation rate. Now, in normal operation, it's not a problem because the cooling water will keep the temperature well under control. That's fine. Now, after a scram event occurs, the reactors aren't actually hot enough anymore to generate steam to make electricity. But they still have some latent heat, and more importantly, they have decay heat. So I mentioned this before. Decay heat is something that it's difficult to get your head around. But when we split uranium or plutonium, nuclear fission, we get byproducts. And those byproducts are themselves radioactive. And as they decay, they themselves generate heat as part of their decay reaction. So essentially, decay heat is the term that describes the continuing nuclear reaction. Despite the fact that the main reaction of the uranium or plutonium has ended, the beta decay of the byproducts of the original fission reaction will still occur. Now, the decay heat fraction is usually expressed as a fraction of the full power of the reactor. And it starts at about 7% of full power, and that's at a 1 second post-scram event. And then it reduces logarithmically. So about 4% at 1 minute, 2% at 10 minutes, but then it really slows down. And it can take about 5 hours to reach 1% of full load and about 0.2% after 10 days. Now, when we consider the size of some of these reactors, we're talking about 768 megawatts. That's a lot of power. 1% of 768 megawatts is still a lot of heat. So if you don't keep it cool, it's going to get very hot. And that's a bad thing. And it takes a long time for the decay heat to actually slow down to a point at which these fuel rods will actually be able to stay cool in free air. Quite some time. Now, all those figures and percentages I just quoted, they're all approximations because it varies based on the type of fuel in question, like if it is uranium or plutonium, and therefore the byproducts that you will get from the reaction. It also depends on the concentration of the fuel and the life of that fuel. Like, for example, newer fuel will have less byproducts. So, therefore, newer fuel will have less decay heat, in theory. So, all those numbers are approximations. But it illustrates the problem, that decay heat is a problem. So, okay, it's critically important that the fuel rods are then kept cool after you have a shutdown for at least a week or two. And so that happens, external power is required to keep the system cool. You need to keep circulating cool water through those fuel rods to keep them cool. Now, ordinarily, that would be taken care of power from the electrical grid that's backfed, what we call in the industry backfeeding. And the idea is that the power grid then supplies the power to cool the reactors. However, in this particular case, all 6 of the high-voltage transmission lines that connected the power plant to the electrical grid were destroyed by the earthquake following the tsunami, and the following tsunami, I should say. Now, the so-called essential service water systems that keep the cooling water circulating through the reactor, they have several other backups. And the backup system installed on site, the ESSs at Fukushima, they had an independent, redundant power system of diesel generators. Now, the generators were regularly tested to ensure they operated when they had to. Their fuel was topped up, everything was maintained. They were, so far as we are aware anyhow, in full working order. When the scram event occurred, the diesel generators were fully functional, even when they lost mains power. However, by the time the tsunami had breached the wall, the diesel generators were inundated with seawater. 11 of the 12 diesel generators failed, and with only one remaining generator off in a distant part of the plant, it was powering Reactor 6. And Reactor 6 was already offline, which we mentioned before. On a positive note, it continued to circulate cooling water through reactors 5 and 6 and ensured there was no incident in those reactors. So that's something. The impact of the tsunami had already destroyed the seawater lift pumps on the ocean side of the seawall because they had been mounted lower and closer to sea level. And there's additional power systems to circulate cooling water. And in this case, there's an emergency backup battery, a UPS system, that was able to power cooling pumps for 8 hours by design. Unfortunately, the flooding from the tsunami destroyed the batteries in Units 1 and 2 because they also were in a low-lying area of the plant. The slightly newer Unit 3 batteries, however, were not damaged and surprisingly lasted as long as 30 hours before they were depleted, which far exceeded their original 8-hour design life. Now, it's common practice for emergency power systems, like those at Fukushima, that there's an external power connection point where you could deliver a mobile, portable, temporary generator that you can then connect in to supply power in a true emergency. Unfortunately, this connection point had been swamped and was severely damaged by the tsunami, and it rendered it inaccessible for several days. There was also difficulty in getting the generator, the portable generator, to the plant. The reactors themselves, for incidents such as this, have two additional layers of protection. A primary containment vessel, which is a steel and concrete reinforced structure surrounding the core, and a secondary containment vessel, and that's usually just the reactor building. And whilst the secondary containment's usually sealed well, it's not reinforced to the same extent as the primary containment vessel. So a bit more about the timeline. At 7:03 p.m. local time, the government declared a nuclear emergency. By 8:50 p.m. that day, the Fukushima Prefecture Office ordered a 2-kilometre radius evacuation zone. By 9:23, the government increased this radius to 3 kilometres and instructed residents to stay inside buildings in the next radius up to 10 kilometres away. The following day, at 5:44 in the morning, the government ordered a full evacuation to a 10-kilometre radius. And then that evening, at 6:25 p.m., the government then extended this to 20 kilometres away from the plant. Around lunchtime, on day 4, following the incident, the government ordered all residents to stay inside buildings in the area between 20 to 30 kilometres from the plant. Over the next 2 weeks, there were a succession of hydrogen explosions at reactor 1, 2, and 3. To list the times mentioned relative from the moment of the primary earthquake, we'll look at some of these events. Units 1, 2, and 3 lost AC power when the generators died at 51, 54, and 52 minutes out, respectively, pretty close together. There were issues with circulating cooling water in Unit 1. So Unit 1, it lost its circulating cooling within 1 hour. Unit 2 and 3, 70 and 36 hours out, respectively. The water level had dropped to a critical height because of accelerated evaporation due to high heat, which is what happens when you stop circulating fresh cooling water. And now, at these points, they were only just covering the top of the fuel rods. So at 3 hours out, 74 and 42 hours for Units 1, 2, and 3, respectively. Because of the low coverage of water and the low amount of cooling, damage to the cores began at 4 hours, 77 hours, and 44 hours, respectively. So each of the 3 cores sustained damage. The reactor primary pressure containment vessel sustained damage at 11 hours. Ultimately, we're only certain of the timing of this for reactor number 1. Damage occurred to all 3, but the timeline for the exact moment of these is unclear for Units 2 and 3. Fire pumps were used with fresh water, spraying the core at 15 hours for Unit 1 and 43 hours for Unit 3. Unit 2 was never sprayed with fresh water, only seawater, because it was essentially, nearly 30 hours later before it had issues. Hydrogen explosions occurred due to Zirc alloy oxidation at 25 hours for Unit 1 and 68 hours for Unit 3, causing significant damage to their own and adjacent structures. The off-site electrical supply became available between 11 to 15 days later and was brought on in stages for different units. Freshwater cooling was re-established 14 to 15 days later for all 3 units. On the 25th of March, the government requested a voluntary evacuation of all residents in the area from 20 to 30 kilometre radius from the plant. About a month later, on the 21st of April, the government set a 20 kilometre radius as a no-go zone for all residents. When the water temperature dropped below 100 degrees at atmospheric pressure, the reactor is said to be in cold shutdown. It's still pretty hot, but it's technically a cold shutdown. The reactor reached cold shutdown on the 16th of December, 2011. That's quite some time after the incident. 9 months. That's how long it took. What's interesting is the neighboring Daiichi plant, Fukushima 2, is located some 15 kilometers away from Daiichi. Now, they were hit by a tsunami as well, of course. It was only 9 meters in height. The height of the tsunami as it crosses the ocean's got a lot to do with the profile of the seabed as it approaches the shoreline. Now, they still had one of their power lines were still available into the plant after the earthquake and the tsunami had passed. So whilst there were interruptions to the cooling supply post-scram, with some of the generators damaged, external power didn't really strictly require them. Power and cooling systems were restored within 30 hours with new pumps fitted for units 1, 2, and 4. And no incidents were recorded at this plant. And it was only 15 kilometers away, a completely different ending. Radioactive releases into the environment as a result of this incident. The main radionuclide released was iodine-131, has a half-life of about 8 days. The other main radionuclide is cesium-137. Unfortunately, it has a half-life of about 30 years. It's easily carried in smoke, tends to settle on land, and contaminates that land for decades. Cesium-134 was also released in smaller quantities, has a half-life of about 2 years. One of the problems with cesium is that it's water-soluble, and when it's ingested, has a biological half-life of about 70 days. Of course, tracking the exact extent of radioactive releases from Fukushima post-incident is very difficult, since the mandatory radiation monitoring stations, of which there were 24, well, 23 of them were disabled by the tsunami. So it's hard to be sure. So nuclear fission seems like such a good idea, or does it? A little bit about the history and why we need the water and why we put these plants where we do, so we can understand why on earth they would put a nuclear power plant where they did. See, nuclear power, the first plant was actually built for civilian use, was a 5 megawatt reactor at Obninsk in 1954. That was in the Soviet Union at the time. Now, since then, many different designs have been tried, many different reactors are in operation around the world. There's actually just under 500 nuclear reactors currently in operation, and they generate 2,731 terawatt hours. And the global total generation as of last year was 20,261 terawatt hours for all forms of energy. So that puts nuclear at about 13% of the world's electricity generation. Of course, some countries like France, it's the vast majority, and the US, it's about 1/5 of its electricity is generated from nuclear. And nuclear is actually, in many respects, no different from coal, oil, or gas-driven electricity generation insofar as it requires cooling water. And the concept is simple enough. Make heat through some heat source. Heat that up. Heat up some highly cleaned water, chemically cleaned water, so as pure water as you can make it, and then turn that into high-pressure steam. That steam drives a steam turbine spins around, drives an alternator, which then generates electricity. From there, we need to cool that steam down and pass it back through the heat source again, because you can't pump steam. So, these sorts of plants are called thermoelectric power plants. And in the United States, for example, 90% of all electricity is generated by a thermoelectric power plant. And cooling water is a very big part of the selection process when you're siting a power plant. Now, not enough water, and you have problems ranging from excessive thermal effects on the local ecology, depriving the local ecosystem of its minimum water requirements, or simply not being able to cool the plant at all, and it's not viable. So, obvious choices include large lakes, large rivers, but if you're happy to deal with the corrosive consequences of living with salt water, then the most obvious choice is actually the ocean. So much so that with nuclear reactors, about 1/5 of them are located on or within 5 kilometers of the coastline. They use seawater for their cooling. So when you consider a nuclear reactor site in particular, there's a long list of additional potential disasters you need to consider. And clearly for Japan, the two big ones were earthquakes and tsunami. And there can be very little doubt based on what happened at Fukushima that whilst TEPCO may have considered both of them, arguably the earthquake risk was adequately covered, but the tsunami precautions were perhaps a little bit less well considered. Before we go any further, I'd like to talk about our sponsor for this episode, and that's Extrasensory Devices. They're an innovative company based in Palo Alto, California, and they've recently released their all-new Luxi For All. It's an incident light meter attachment for your smartphone or tablet. If you're a photographer that likes to take the best possible shot, or even if you aspire to be a better photographer, then precise control of your exposure is critical, and to figure that out, you need a reliable and accurate light meter. Standalone light meters can cost $100 or more, take up a lot of space in your camera bag, they need their own batteries, and they can be a pain to use, but the Luxi For All aims to solve all those problems by utilizing the front-facing camera on your smartphone or tablet and provides accurate readings using its freely available Luxi app from the App Store or the Google Play Store. Luxi For All is easy and quick to calibrate on your first use, and you can set and forget. With spot metering and incident light modes, the Luxi app will suggest ideal settings for f-stop, time, and ISO settings on your SLR. Or you can lock or unlock any of those, and it'll figure out optimal values for the other settings. The Luxi For All is a passive device, so there's no batteries you have to worry about. It's small, measuring just 1.5 by 1/2 by 1 inch. That's 38 by 13 by 25 millimeters, and it's light at only 1 ounce or 28 grams. So it fits nicely and easily in your camera bag. It's really easy to put it on and take it off, and there's a nice touch in the Luxi app that detects when the Luxi is attached and automatically changes the mode of the app to light monitoring for you. I suggest before, it's not as expensive as standalone meters. It's only $29.95 US, and if you'd like to check one out, just head over to esdevices.com/engineered to learn more and enter the coupon code ENGINEERED for 15% off your Luxi For All. Photographers always want to take better pictures, and taking better pictures starts with your Luxi. Thank you to Extrasensory Devices for sponsoring Causality and the Engineered Network. So what design flaws were present at this plant? It's quite disturbing when I was doing the research on this, because I do understand to an extent how they reached the conclusions that they did. But it doesn't make it that much less terrifying to me personally. The plant was actually constructed on a bluff, and that bluff was originally 35 meters above sea level. Well, they decided to take 25 meters off of that height. It may sound crazy, but I'll tell you why. The license for the plant and basis of design was that it only had to withstand a 3.1 meter maximum height tsunami. But that design basis was based on an earthquake that happened in Chile in 1960, and that resulted in a 3.1 meter wave halfway across the world at Japan at the current construction location at Fukushima. Japanese researchers have increasingly found more evidence of sedimentation layers far inland from that location, and they suggest now that large tsunamis of the size seen in 2011 can actually occur approximately once every 1,000 years in that area. As more evidence mounts in recent times, there were concerns raised within TEPCO after the construction about the tsunami risk to the plant. In 2008, TEPCO performed some computer simulation modeling, and they determined the risk to the plant may have been underestimated after all. Now, NISA is the Nuclear and Industrial Safety Agency in Japan, and NISA were first provided the details of TEPCO's simulation models, interestingly, 4 days before the tsunami struck. That's one of those unpleasant coincidences. So 3 years after the analysis was performed, they provided it to NISA, which is interesting. Anyway, back to the construction phase. So during construction, TEPCO decided to lower the height of the bluff by 25 meters, as I said. And that made the base plant level at about 10 meters above sea level. still well above their 3.1 meter maximum design height. The reasons that they quoted for lowering the bluff included to allow the base of the reactors to be constructed in solid bedrock, and that mitigated earthquake damage. Now, people that are aware of civil engineering in earthquake-prone areas understand that bedrock is an ideal material for you to be placing your structure because bedrock cannot go through liquefaction when the ground vibrates. Not going to talk about liquefaction. But if you were to put a build it on sand, what happens under a high vibration situation like an earthquake is that sand essentially starts to act like a liquid, and anything in it tends to sink. Very quickly, in fact. Sand, dirt, it's a problem. But bedrock is solid as rock. How about that? Now, it had to be about something else too, didn't it? The running costs. The seawater pumps needed to lift the water from the sea to cool the plant. The higher the plant is, the bigger the pumps needed to be because they are pumping against a much higher head pressure. And lifting all that seawater the much larger distance would have much higher long-term operating costs. Maintenance costs also would be higher for the pump maintenance, and it would just be more expensive as a long-term operating cost. So by lowering the height, you reduce the distance you have to pump the water, makes it cheaper. Now, TEPCO's analysis of the tsunami risk determined a 10-meter high seawall would provide protection for the maximum tsunami assumed by the design basis. The diesel backup generators that were most likely to be required during an earthquake or tsunami event were located in the basement of the turbine hall, and that was only 10 meters above sea level. Now, putting generators at those lower heights, it certainly makes them cheaper to construct, and it's easier to maintain them if you have to do any work on them. And you do have to strip these things from time to time and maintain them. Now, most buildings that I've worked on, the overwhelming majority have their backup jennies in the basement, or in the ground floor at least. But there was one building in particular that I remember. They put their gen set on the 9th floor of the building. It had a diesel fuel day tank on the 9th floor with enough fuel in it to run for, oddly, as the name suggests, a day, with a bulk fuel tank had enough in it to run for a week, and that was in the basement. But that was their compromise. At the time, I remember arguing with them that with the building's additional reinforcing to handle the mass of the diesel generator, putting the bulk fuel tank on or near the 9th floor would have actually finished the job. The tanker truck could have had a low-lift pump, a more powerful pump to actually pump the fuel up to the 9th floor when it was filling up the bulk fuel tank, but they decided not to do that. Irrespective of that decision, you would have to put a sealed containment bund around the bulk fuel tank as they had around the day tank, but it could have been done. So in an inundation event, if it ever happened, it would then be totally protected and isolated. That's not what they did. Ultimately, though, that's not the point. It's a common practice to put generators at ground level or in the basement. And honestly, it's pretty stupid. I've always thought that. I don't get it. Because when you need it in a flooding event, that's not going to work, is it? Same with switchboards for that matter. Now, if you don't raise the height of the genset, it's not the end of the world. There's other things you could do. You could put them in a watertight bund. And by bund, I mean it's a wall around the outside without a lid on it, essentially. No roof. But then I think to myself a little bit about the Titanic's interlocking doors. Now, how high is high enough to make that wall high enough to stop becoming inundated? And the next question is, if you do put a wall around it, you're stifling the cooling. So are you going to have enough? Are you going to have adequate cooling for the generator trapped inside its little box? What about access and egress when you need maintenance? You need to pull out the alternator. You need to pull out sections of the motor for maintenance purposes. It makes everything like that more difficult and more expensive. So they didn't do that either. Now, the seawater low-lift pumps were also a big part of this. The intake and the building for the low-lift pumps was set at 4 meters above sea level, which was above the maximum tsunami design height. But these were the only mechanisms available to draw water in from the ocean, and you needed that cooling water. It was your cooling water source. they could have added a backup system with multiple intake heights from different depths, with a lower speed, smaller size pumps that are just designed to handle post-scram cooling. The requirements of post-scram cooling are not as great as when you're in full operation because you're not at full heat load. So you don't need to cool as much water, so you didn't need as big a pump. Well, they could have done that, but they didn't. The other option, of course, they could have mounted them higher with a more reinforced structure. Mind you, that would have cost more money. Refer previous comment about the higher pumps, higher head pressure. So obviously, you want to mount them closer. In the aftermath of this incident, in fact, in March this year, the Japanese National Police Agency confirmed, as a result of the earthquake, there were 15,893 deaths, 6,152 people were injured, 2,572 people were reported as missing. Staggering number, though, is 228,863 people displaced from their homes, either temporarily or permanently. A large number of those relate directly to the exclusion zone around Fukushima. Now, in amongst those figures will be individuals affected by the incident at Fukushima. Of course, plenty of other people were affected by the tsunami directly. And this isn't a show about preventing natural disasters, since you can't. But in engineering, we design and we construct buildings, roads, control systems, electricity grids. We design all these things to withstand natural disasters of a certain intensity. If we build something that can't withstand a natural disaster, I want to know why. Ultimately, the incident's being compared to Chernobyl, and TEPCO officially stated that the amount of radioactive material was only about 15% of that released at Chernobyl. But the truth is that this figure is kind of, well, I'd say highly questionable, because it's very difficult to accurately determine that. Access to those cores at Units 1, 2, and 3 is still not safe, and it won't be for many years to come. It's going to take 30 to 40 years to clean up the fuel and remediate that site. In the 20-kilometer no-go zone, it remains in place today, and it's 4 years after the incident, and it's going to be in place for a very long time. I came across a very eerie set of photos taken by a brave, maybe, photographer, and some from an aerial drone as recently as a month ago, and they're both stunning and terrifying at the same time. There's a link in the show notes, and it's called the Fukushima Wasteland. It shows how nature is taking over again. There's abandoned cars, overgrown by weeds on a freeway, it looks like. Grasses and sidewalks hidden by foliage. Tables that were still set with half-eaten meals on them. It's going to be 3 decades, at least, before they could potentially declare the area safe. And even then, that's not a certainty. There's a lot of disagreeing information about what happened at Fukushima. A lot of it is because we're not sure how transparent TEPCO has been. A lot of it is because of misinformation spread on social media. Spent quite a bit of time trying to get to the truth of exactly what figures and what happened when, and it's quite difficult. The reality, though, is that no matter how you slice it, they made the wrong choices when they designed the plant. But it comes back to the design basis. A 3.1 meter tsunami, to me, sounds insane. Japan is perhaps one of the most dangerous countries to live in regarding tsunamis and tsunami risk. And 3.1 meters is not very big in terms of tsunami wave heights. So whilst it was a huge event, as the evidence mounted in subsequent decades, it wasn't really reassessed seriously until 2008. And even when it was, they were considering raising it to, I think, 5.7 meters or thereabouts was their design basis adjustment for the maximum tsunami height. And even if they had have taken precautions to protect against that, it still would not have been enough. So the problem is, when you say on a design basis, I want it to withstand a storm event of 1 in 1,000 years or 1 in 10,000 years events, so something extreme. How do you know if the history doesn't go back that far? Just because you find sediment 2, 5, 10 kilometers, miles inland, that doesn't tell you how big the tsunami wave was when it hit the coastline. I mean, computer modeling will help, sure, but you just don't know for sure. You know it was bad, you just don't know how bad. And if you don't know that, how can you be sure you're meeting that requirement? So what do? We fall back on the most recent sample of history, which is only, when the plant was designed, it was 1967 it was first constructed, Unit 1. And we only had accurate records going back to 1900 in terms of earthquakes, related tsunamis, and the height measurements. We just don't have the history. How do you know it's enough? History repeats itself. But that's only useful if you're measuring history, if you're recording it. Nuclear fission, I guess, is most analogous to an enormous explosion in extremely, agonizingly slow motion. The problem is that once you start that reaction, that fission reaction, your goal at that point is to slow it down and keep it under control. Because if you can control it, you can use the heat to make as much electricity as you like. Problem is, if you screw it up, it doesn't take very long for it to get out of control. And once it's out of control, bringing it back under control is extremely difficult. It takes many, many months, in some cases years, and there are serious consequences if you get it wrong. We should be reassessing the protective measures as a result of global warming, because those effects are starting to be felt, especially with rising sea levels, for plants like this. And there's a lot of them. In the last 2 decades, in case you thought that Fukushima was an isolated case, it's not. In the last 2 decades, there have been several other, call them beyond design basis flooding, if you'd like, earthquake-related, some of them, at different nuclear power plants around the world. So let's go through some of them. December 1999, a storm surge caused flooding at 2 reactors at the Daiichi Nuclear Power Plant in France. On December 26, 2004, that was the Indian Ocean tsunami. That flooded the seawater pumps at Madras Atomic Power Station in India. On the 16th of July 2007, an earthquake exceeded the design basis of TEPCO's Kashiwazaki Kariwa nuclear power station in Niigata Prefecture. On August the 23rd, 2011, several months after Fukushima, an earthquake on the east coast of the United States marginally exceeded the design basis of the North Anna Nuclear Generating Station in Virginia. None of those led to a significant incident. No radioactivity was emitted. Call them close calls, perhaps, or cautionary, if nothing else. I guess no matter how many times I go through this in my mind, I'm just not convinced nuclear fission can ever be risk-free. There'll always be risks. There'll always be things we just cannot foresee. We can't account for. And we can't protect against. Ultimately, the cost of solar and wind power is coming down every year. And as we step closer to truly solving the battery problem for storing that power overnight, maybe we can finally stop playing with nuclear power and pretending that we're in control of it. Because we're not. I'd like to thank Extrasensory Devices and their Luxi For All for sponsoring Causality. Visit esdevices.com/engineered for more information about their handy Luxi For All and use the coupon code ENGINEERED for 15% off, exclusively for Engineered Network listeners. Taking better pictures starts with your Luxi. This was Causality. I'm John Chidgey. Thanks for listening.